Notes 2.4 are about limits at infinity and horizontal asymptotes. So first we'll talk about limits at infinity. So here we're going to talk about a function f on the interval from a to infinity. If we look at the limit as x approaches infinity on f, it will equal L, means that the values of f can get really close to L if we make x really large. So saying x approaches infinity could be done by hand by making x really large. So we can't make it infinity, but we can make it a large number. And then the same is true if you take the limit as x goes to negative infinity. So if the limit equals L, that means we're getting a value for the function as x gets sufficiently large. So we're going to go through that process with this first example. First, we will take x sufficiently large. So when x is 10 and you substitute 10 into the function, you get 0.058. Then 100 gets you 0.010. 1000 input gives us 0.001 output, and so on. So as you can see, as the x's get larger and larger and larger, the y values get closer and closer and closer to 0. So we can write as x approaches infinity, comma, f of x approaches 0. That's one way to write it. Or you can write the limit as x approaches infinity of f of x equals 0. Now let's look at the same function but taking x sufficiently large negative. So I've already picked out x values that are getting smaller and smaller and smaller. Let's see what kind of values we get. So evaluate f for negative 10 and we get negative 0.136. Negative 100 gives us negative 0.0104, then negative 0.001, and so on. So here again, as x approaches a very large negative number, the y value gets closer and closer to 0, but it's coming from the negative side. So we can write as x approaches negative infinity, f of x approaches 0. Or another way to write that is the limit as x approaches negative infinity of f of x equals 0. There's another observation we can make, and that is about a horizontal asymptote in this situation. Because what's happening is the x values are approaching an infinity, but the y values are not. So when one of your variables is approaching infinity and the other one is approaching a number, then you will have an asymptote occurring. So in this case, the case we're working on, the line y equals L is going to be a horizontal asymptote. So this is what it looks like to observe a horizontal asymptote. I'm going to give you a very common example. F of x equals 1 over x. This function is going to be very important to us, so it's nice to keep examining it whenever we get the opportunity. So I'm going to start with the table and look at these values of x. When I substitute 10 into the function, I get 1/10, and then of course 1/100th, 1,000th, and so on. So as x is getting very large, f of x is approaching 0 in this case as well. And again, I can write as x approaches infinity, f of x approaches 0. But of course, we would want you to write it in limit notation. So the limit as x approaches infinity of 1 over x equals 0. And by our horizontal asymptote definition, this means, therefore, that y equals 0 is a horizontal asymptote of the graph. Okay, I decided to look at a more interesting example. In the denominator, the dominating term is 6x squared. So you can argue as x approaches infinity, the quantity 6x squared is also approaching infinity. So it looks like the limit is infinity over infinity. You need to know that this is not equal to 1. This is actually something we call an indeterminate form. When we have an indeterminate form, we need to try to do something else. So we usually look at algebra as a possibility. So the algebra move I'm going to do is I'm going to divide the numerator and denominator by the highest powered x. So I'm going to divide numerator and denominator by x squared. So it's going to look like this. So I'm going to do division in the numerator and I'll do division in the denominator. And now applying the limit law, I can take the limit of each of these terms. So the limit as x approaches infinity of 2 is just 2. And then the limit as x approaches infinity of 1 over x, we just learned, is 0. So that was from an example up above. And then the limit as x approaches infinity of 1 over x squared, that's going to equal 0 also. So we get 2 minus 0 plus 0 in the numerator. Now let's take the limit as x approaches infinity of 6. That will always be 6. And then the limit as x approaches infinity of 3 over x is going to be 0, just like in the previous example. And the same thing is true for the last term. So we end up getting 2 divided by 6, which is 1/3. Therefore, y equals 1/3 is a horizontal asymptote of the graph. You are allowed to use HA to stand for horizontal asymptote. Here's a better description of when you have a horizontal asymptote. It comes from an Algebra 2 perspective. So we're going to look at f as the quotient of two polynomial functions whose leading coefficients are a sub m on top and b sub n on the bottom. So if you find out that the power of the numerator is less than the power of the denominator as x approaches infinity, then the horizontal asymptote is y equals 0. So that is the case in the example that we did right here, this example. The degree of the numerator is 0, the degree of the denominator is 1, therefore the horizontal asymptote is y equals 0. If the degree of the numerator equals the degree of the denominator, then you end up getting a horizontal asymptote that is the quotient of the leading coefficients. So go back to the previous example and look at those leading coefficients. The numerator was a 2, the denominator, the leading coefficient, was a 6, and we ended up getting 2 over 6, which reduces to 1/3. Finally, you could have a degree in the numerator larger than the degree in the denominator. So as x approaches infinity, the numerator will dominate, and then the value of the function will increase without bound. So there is no horizontal asymptote, but there could be a different kind of asymptote. M and n, if there's only a difference of 1, then you'd have a slant asymptote. If it was a difference of 2, then you'd have a parabolic asymptote, and so forth. I chose another example. This one has the same idea as the last one, but there's a little twist to it. Notice that this looks like there's an x squared in the numerator and an x in the denominator. It looks like the degrees are different, but they're not. In the numerator, we actually have the square root of x squared. So that behaves like an x when you actually graph it. So if we just analyze a little further, if we were to substitute, if we tried that substitution idea, if we thought of x squared as increasing without bound, this looks like an infinity over infinity situation. So what I'm going to do is I'm going to divide by the highest power, which is x to the first power. Or, like I just stated, it's the same as the square root of x squared. Sort of. So let's look at that first, dividing top and bottom. So I'm going to take the quotient of the limits. So I'll divide the square root of x squared minus 5 by the square root of x squared, which is like x. And then in the denominator, I'll divide by x. Okay, so first I'm going to divide x squared by x squared, and I'll get 1. Copy the minus, and then I'm going to take 5 divided by x squared. I can take the limits on each of the terms. So I'm using a couple of limit laws here. In the numerator, the square root symbol means there's a power of 1/2, so I can take the limit inside of the power. So I'm going to ignore the square root for a moment and just take the limit on 1, which is 1. And then I'll take the limit on 5 over x squared, which is 0. So in the denominator, the limit on 2 is 2, and the limit on 3 over x is 0. So I end up with the square root of 1 over 2, which is 1/2. Therefore, the horizontal asymptote is y equals 1/2. But wait. The square root of x squared is x when x is greater than or equal to 0. And the square root of x squared equals the opposite of x when x is less than 0. So we must divide by the opposite of x also. So I'm going to go through the same steps of taking the quotient of the limits, but I'm going to do it with the opposite of x. There are actually 2 horizontal asymptotes for this graph. So go on your graphing calculator and enter in the function f of x equals the square root of x squared minus 5 over 2x plus 3, and take a look at what that graph looks like.